Greetings, everybody, and hello. My name is Kevin Kocak. I'm the founder CEO of Chemical Q Device. Here for this is Monday, December 2nd, 2024, number 152. So this focuses on monoclonal antibody bioprocess engineering in context table forecast primarily, using and supplementing it with literature, like facts from literature, and this goes into the decision based on what other authors have found. So the first thing I'm going to start off with here are the speed ups. So for each of these tasks, and you see these three different sections here. For the first section, it's about real-time search. And so what I had is the ChatGPT 4.0 search section. And then I also had the Perplexity GPT 4.0, Perplexity 3.5 Sonnet, and then the new computer use by 3.5 Sonnet. And I also did the same tasks, right? Same or similar, or sometimes the generative AI does a lot more than I do. And this is what I found is basically for multiplier speed. So this is based on the raw time, and then it's adjusted for words. So you can see typically my outputs are much smaller, 178 words, and then my times are much longer, right? So 190x for ChatGPT 4.0s, that's that globe feature. If you click on the globe, Perplexity GPT 4.0 was 177 times faster than mine, and the 3.5 Sonnet 87 times. Now, the computer use or this agent or this agentic model by 3.5 Sonnet that you click through, you have to use Docker desktop that you click through, that was not good at all. I tested it so many times. I tried to fix, settings on Docker desktop, and it times out, but you get a lot of these screenshots that kind of shows you what could be in the future of how these models interact with your computer, more thinking of things agentically, even though other models are thought to be agentic as well. So that's shown here. So basically on the right-hand side are all these speed ups. So you see that 177x coming off the Perplexity GPT 4.0. And then these go all the way up to this bottom section for over 400 and then over 600 times faster. Now in that second section is basically I read the abstracts and it reads the full papers. And then we both answer similar questions. So the speed ups were more modest in this middle section here, just because I can do this efficiently. I can read an abstract efficiently, and I can write a paper efficiently in the course of, 400 or 500 seconds, something like that. So 5 to 7 minutes to 9 minutes, something like that. And, so we see a lot of these multipliers, being anywhere from like 60 to like 144x, so not substantial. Now, the one that really shines is this last one for the AI models, because it takes me so long to read this paper. It's a review paper. And, so basically it takes me like almost 10,000 seconds to read the paper, write a response, typing it. And in this specific case, I had it do additionally like 3 times to explain itself, like how exactly did you get this answer? And it says most of the cases in this, it's using advanced natural language processing and other standard techniques like document search, as opposed to other advanced types of processing and other advanced types of machine learning inferencing, which was kind of interesting. So in this specific section, I did not, have to answer that because I'm a human, and it answered it according to its best that it could. So this multiplier speed was based on the speed that it also took me, and not these other kind of prompting to figure out how exactly it solved these questions. So yeah, like 25 speed ups in that previous slide. So this one is basically, these are the protocols used in this specific paper. So you see in this first one, I'm using a specific paper and I'm getting out, the forecast based off of it. And I'm getting supported by 2 other papers, this paper 3, paper 7. And then again, using those methods to say, how can the author's results in paper 2 be improved? And I had to pick out the weaknesses in the paper as far as what they were and what the other 2 papers could improve on. And likewise, I did this for paper 3, supported by paper 2 and 7, and then paper 7 supported by paper 2 and 3. Now, these next 2 are based on big tables. So this was extracellular table here. I first take the original paper, the main paper that has the table as a supplement to be used later, and I identify its weaknesses. And then from there, I use extracellular table, get a forecast of basically what an LLM, how it could help in the future. And then I take it a next step further, the next prompt, and I incorporate 11 paper summaries and get those author methods, and then utilize that to say, okay, based on all of this information, based on all these other authors' methods, and this LLM projection of what it could do in the future, what is the final response for that? The same case was for intracellular table at the bottom here. The extracellular table I'll show you, it's 136 metabolites. And I chose 4 of the 6 columns to focus on. And the same thing with the intracellular table, 4 kinetic time points. Even though I processed the whole table, it's not going to have that processing power to do relationships across that many variables. So in this specific one, so this is the, this is part 1, is, you see with the scores, so ChatGPT 4.0 did a little bit better, and I compared these, and the conditions are in the paper, and they go through anything from like, how well did it cite the original author's numerical values and quotations? And then it goes, through these other 3 different conditions as well. So they performed solidly. So this feature that I'm using is called document retrieval or document search. And on ChatGPT 4.0, this is the plus icon. And then in 3.5 Sonnet, it is the paperclip option. And in 3 Opus, it's the paperclip option again. And what it does is it processes the whole PDF, pretty well. And it's a feature that's not used on O1 Preview yet, which is kind of like the dominating model as far as like this advanced reasoning. So we see all of these perform very solidly. And like I said, this first section here is paper 2 backed up by the other 2. And then the second section here is paper 3 backed up by the other 2. And then the third one is paper 7, get the LLM forecast, and then backed up by the other 2 as well. Pulling in these other methods from these other pieces of literature to add strength into saying, okay, this will be improved by if we use other papers. Hence, conversational AI and large language models, their strengths of using. And here's the 3.5 Sonnet. So it addressed these weaknesses of other authors. And I included a Claude model, which is by Anthropic. Like I said, the ChatGPT 4.0 tended to do a little bit better, even though I gave this one a score of 9.0. You see it goes through and it starts to talk about the other authors. And the 4.0 didn't do well. And I wanted quotations from the original numerical values. So in specific with this one, it says DO, which is dissolved oxygen, levels dropped from 50 to 10% at approximately 90 H or hours. And it did that, more efficiently. Now the 3 Opus, which is also a Claude or Anthropic model, it did good at that too. And it tends to have less of the kind of the meaty substance that this had, but it's more in paragraph forms. And like I said, with the ChatGPT 4.0, it tended to strike the better balance. But still a really good response. And I tried to keep the formatting as close as I could. The full generations are in the supplementary files associated with the ChemArchive submission, or that's up right now. Now, here are the 2 tables. So this is the Sakwatanan paper. And I focused on these because inside these, okay, so there's 3 main sections. So you have Chinese hamster lung, for each of the, a cell pool for each 136. Then you have Chinese hamster lung, and the ones that I focus on, and they call it B08, or it was the main line that was focused on this particular paper. They also looked at Chinese hamster ovary. So in both of these tables, again, I processed them fully as CSVs, comma separated values. And the questions that I asked were based on 4 of the columns for each of the 136, if it could generate the 136. And then also for the second one, if it could generate the 101, which O1 Preview did. And so that basically this is the extracellular part. So again, the paper 6 is the second one paper. Identify the weaknesses, introduce the table, and then get a forecast, and then go back as a second prompt, get a bunch of these paper summaries, which are generated from other similar types of papers, pull those author methods out and then get the new forecast is that specific protocol right there. So you see the O1 preview in this did substantially better than the other models. There was one case where 3 Opus did get a 9.0. It tends to be like a more advanced reasoning one, but it doesn't have that quite that balance or like that convincingness that the O1 preview does with a lot of the facts and, crossing a lot of these check marks off the box. So we see that with the score, with that gold score with the O1 preview. Okay, so this is actually a single generation here. I had to show it like this for illustration purposes. And what it chose to do in this specific case, so again, this is the 136 extracellular metabolite table, is it couldn't process the whole thing. It actually said, here, I'm going to try to have this for you for download, but it's probably something either restricted by OpenAI or some type of processing limitation. And again, I try to be concise with 4 kinetic values. So this is O day is the original author's day 2. And then right next to it, it generated, so the forecasted day 2 of the new values. So if you look at something like arginine, where it improved from O day 2 to F day 2, 1.04 to 1.20, it's saying that this has expected breakthrough. And it's based on the original author and Zhang et al. And it goes through other authors like Bokelman, and there's Crunch and Okamura. These are other papers as well that were used to get their methods to say like, okay, these are the original values, these are the new forecasted values. And then in this specific case, it says it couldn't represent all of the ones that didn't have breakthroughs. Plus those values didn't change anyway. So what it did is it picked the ones that for sure did, and every one that had an expected breakthrough, O1 preview showed in this, I think it's like 18 or 19 metabolite explanation or table here. Okay, so again, it goes author's original value from the original table that I showed you on the previous slide, and then O1 preview is forecasting it, and then O1 preview says, these are the authors' names that support my forecast. Is a breakthrough expected? Now, on top of that, it goes over and it says for each of these, so for arginine number 29, which is right here, arginine number 29, we see increased forecast values due to targeted amino acid supplementation in the original author's papers and nutrient optimization from Zhang. So if I look back over here at the table, it says the original author plus Zhang. There's the breakthrough. There's the explanation based on the papers, okay? And then if I go down further, I can also support it by author name. So the original author was the Sekwatanan, and then Zhang et al., which was also mentioned up here, I can search by author name. It says nutrient feeding optimization to address nutrient insufficiency and improve productivity. So what's happening here is it's pulling all of this information from these 11 paper summaries, and then also the original weaknesses that were identified, while it's looking at this 136 metabolite extracellular table. And I asked basically for the second one, this is a 1 prompt, paper 6, weakness identified. And then this is a second prompt, these ones in the middle. And then the third one is basically saying, okay, so here's your final answer. So I was pretty impressed with this. And again, I gave it a 9.5. A lot of the conditions that I set, that it exceeded my expectations in that I could search by metabolite level, and I can also search by author name. And it jives really well with the chart. Unfortunately, I found one incorrect value with this for one of the original days, but this is a lot of information that we're seeing the LLM effectively process. And, usually you go back to the original papers and you can find this, pretty easily. So it's one of those computational advantages that humans that we don't have. And if you figure, if you were to ask how many number of items there were in a big thing, it's easy for a computer, but it's hard for a human. Okay, so this is the intracellular part, and in this specific one, the table was much smaller. So again, this is the table I'm talking about now. The one I was talking about here. Again, on each of these, I'm only asking for four kinetic columns. even though I'm processing the whole table, I can only ask it. Again, LLMs are great at like high contextual awareness and sifting through papers, but at that same time, there's limitations, just like the curse of dimensionality that still exists today. So so in the second part here, this is what I'm looking at is the intracellular, the smaller table. It has 101 metabolites. So as you can see, the O1 preview did well. And then, like I said, this is the one, 3 Opus. I was actually kind of surprised that it did well. A lot of its responses were longer than most of the other ones. The other models here that I'm showing, I use ChatGPT 4.0 from before. Herm is this Hermes 405 billion. It's a fine-tuned model of the Llama 3.1 405B. Now, this one, they actually had it FP8 or floating point 8. So I think that's what limited it. And it just seemed to have restrictions, in inferencing through, it was called deepinfra.org, I believe. And 3.5 sonnet from before. The Llama 3.145B has a reliable source that I use. It's called fireworks.ai. It's a true open source model under the Meta Llama, community license. And it basically, like, if you had the resources, you could do all sorts of things. But it's a very substantial model. This is like way beyond anything, especially the full model of a capable laptop or even, many professional computers. Like, we're talking about closer to terabyte of RAM than it is a terabyte of storage, even though you need that in storage as well. So these other models didn't perform as well. And based on other studies that I performed with the O1 preview, I was kind of expecting this. And it actually returned the full 101 table. Now, in this specific case, it didn't include much text. So you see the text is all there. I put manuscript author because it kind of sandwiched in between, and based on my formatter, I could only get it to work like putting the table at the bottom, basically. So this is the full 101 table, and it should line up. Again, I couldn't find any incorrect values here. So it spent all of its time doing 101 of these metabolites, original day. Now, the format it shows on this one, original day, and then it went 2, 3, 4, 5, so 4 kinetic time points. And then it chose the forecasted ones after that. And I didn't specify how I wanted it, and either way is fine. And again, it goes through and it says the breakthrough is expected here too. Now, this is coming from a prompt that is earlier in the chain. So there's none of these other original 11 papers also being considered with this. So it actually did most of the things it was supposed to do correctly. And it's primarily based on the original author's paper and the original 101 metabolite table as well. And again, so this is shown below here. So it's, like I said, for the ones, so if I find like an arginine, in here, again, these are intracellular. So typically you start extra and you go intra. So some of the metabolites will change. But again, it did everything pretty much that I asked it for. And again, does it anticipate and breakthrough based on if an LLM, could help it on this specific one. So where everything is today, so what I just showed you is bioprocess engineering. And this all started back in July, okay? So I did 4 different reports in July, and they were all synthetics. And there was other people that had led, with LLMs with this, and I would say definitely Bran and Chen. There's also Ramos too. And a lot of that work was iterative, based on different types of prompts, new model upgrades, using document retrieval to a high level, and also doing, organic syntheses. I focused on 3 of those documents, and then there was a JAX paper in there, and then also a Nature Communications paper, open source, that I chose as well. And then the 5th one, I believe, I can't find anything else that kind of refutes this, large multimodal model chemical research with document retrieval, is the first big manuscript. So this was in August. And, so basically I fed it all these 1D NMR, proton carbon, 2D NMR, mass spec, like calculations, and like another ESI mass spec, kind of like a diagram. So half of it was image-based and half of it was text-based. And according to Ramos, who I mentioned, They didn't believe there was a LLM spectrometric applications yet as of June. So then there was 2 months after that, and then all of this stuff. And I did, the Google search. I couldn't find anything. So then I kept with the spectrometry, or it's technically spectrometric determination, in this next one. And it was the first one I could find that it was quinoline, which is C9H7N. And in this particular one, I gave it a spectra, proton NMR, carbon, and then the 3 depth spectra. And 3 of the OpenAI models correctly identify quinoline. It is a relatively more common molecule, but still to have those 3 backing it up. And, a lot of it, this was like a GPT-5 preview that I used as well. That was very encouraging. And this is done 2 steps. I upload the images as a single image, and then I put in a prompt, and then I push send. And it was a problem based online. And, I think it was UCLA Web Spectra. I asked if I could use it. And they said, yeah. And, so I get this answer, and it's within reason to think that this software, the multimodal part of it, can do that type of processing and have text, because I also had to include the molecular formula as well. Now, number 7 was a big one. And basically, I took 13 of these mixed spectral data, and it was UC Irvine, again, open source. And I asked, I was like, it wasn't able to convert spectra into text right away, but I converted it into text. Like, I analyzed all the 2D and 1D NMRs and IRs, and, there's 13 of them. And 3.5 Sonnet, and after I published O1 Preview, both had the same answer of it's ethyl ester ibuprofen, a smaller molecule at C15H22O2. And I double checked that. I believe it's right. And it's still an unknown that the professor hasn't published the answer for. But again, I had 2 models that were convincing, and based on the data and the correlations, I'm pretty convinced that that's the answer too. Paclitaxel was the breakthrough, because I took the original, so paclitaxel synthesis, like total synthesis, has been done since like the 90s. So this is where I had to switch to biosynthesis. And on this particular one, I chose both historical and emerging answers. Historical meaning if I just gave it a direct prompt, what does the LLM know? And then emerging is based on all these other papers. And there was 10 recent papers on paclitaxel biosynthesis. And this is covering retrobiosynthesis and paclitaxel. I was covering top 10 new areas in paclitaxel biosynthesis, top 10 challenges, and also the engineering, how to engineer organisms. So there's a lot of substance in there, especially in the supplementary too. Now, the number 9, which is the last one, that's monoclonal antibody bioprocess engineering advancements. This is basically using, tables too, and 16 recent papers, multiple speed ups, forecasting, kind of creating an official way to have a human versus AI and in these types of tasks, because I can read and I can write and I can time myself just like I can time it. So that's where a lot of that started, kind of like officially, as far as the versus the human and getting that. So yeah, a lot of data mining, and the tables, it just wasn't as big, but yes, it was forecasting different values at different points. And then obviously with this particular one, with the 25 speed ups and the O1 preview, definitely leading the way. It'd be awesome to see if they start to incorporate some form of document retrieval with that, and increasing the context window as well. Okay, so next study is focusing on drug discovery tumor microenvironments. I've already got a head start on that. And I hope everybody has a great holiday season. Again, this has been 152 episode for Monday, December 2nd, 2024. Have a good rest of the week, and have a productive rest of the day. Take care.